Our next speaker is Professor Ruey Tsay, who is HGB Alexander Professor of Econometrics and Statistics at the Booth School of Business, the University of Chicago. Professor Tsay is elected to Academician of Academia Sinica in 2002. He's going to talk about a new class of Copula models he proposed to capture time-variant dependence across large panels of financial assets. So let's welcome Professor Tsay.
Oh, thank you for the introduction. It's my honor to be here, and thank the organizer for organizing this interesting conference. What I'm going to talk about is talking about a Copula model for high-dimensional asset returns. Some of the application we have in mind is try to quantify the extreme dependence, like the Kendall's tower and so on, so you can, when you calculate the value risk or expected shortfall, you can combine all the assets together. For example, you worry about systemic type of risk, and you can handle a large amount of financial institution, and you can analyze this type of problems. So that's what we have in mind. Now basically, we summarize what we did in the paper. We built a factor Copula model with time-varying dependent structures. It's a highly structured type of model when the dimension is high. So we focus on high dimension, for example, like 100 or above that. The model we propose is a general type of factor model, but it's flexible in some sense. So you can cover the Gaussian Copula model, student T, or group student T type of Copula models. The estimation is based on the recent development called the particle MCMC type of methods. The idea is once we have factor, based on the factor structures, you can leverage that to estimate model in high dimensions. The factor, in some sense, simplify a lot of calculations. In the application we have in mind, the demonstration, we focus on 100 US companies, the daily return from 2008 to about February of 2013, last year. We also try to combine information together from different markets. So we try to analyze the asset return as well as the CDS returns. So in that sense, we have 200 dimensions. So 200 model 200 dimension type of asset returns. So if you think about correlation, there are tons of correlation there, and those correlations are time varying. We like to model them. The model we talk about is also flexible. For the marginal model, the univariate model, even though we have 200 assets, you can use flexible model. So we use stochastic volatility model with leverage and heavy tail type of distribution. So marginal model, you can use for a flexible model. Once you have flexible marginal model, you try to put into the Copula, and there you can use a factor model to simplify the structures. So that's basically the idea we have. In terms of using Copula in financial econometrics, it's been around for a long time. The first one may be David Lee before the financial crisis using the Gaussian Copula model, and maybe the first one. After that, many people are doing that. Of course, you have time varying type of Copula. People use that. Typically, the time value type of Copula was available. The seen side here are relatively low dimension. In terms of Bayesian inference in Copula, they also had some research. The Smith 2011 that provides some survey, so you can look at that to understand what the Bayesian method available in doing Copula type of estimations. Of course, high dimensional model of the CDS is not new. People working on that too. So those are basically related literature, just try to, some sort of like our work related to the literature in this way. Now, Copula is just a simple idea to model the dependence between variables. It's based on, you can write it in this way. It's just a distribution function over the hypercube in the n dimensions. And the UI are uniform 0, 1. Because you use a marginal, you can use a probability integral transform to transform to uniform. The key theorem here is for any joint distribution function, f is n dimension of random vectors. It can be decomposed into Copula and the margins. So basically, the pi are the marginal cumulative distribution function. So in that sense, the Copula C is just described dependent structure of the joint distributions. So that's a basic concept. So to thinking about dynamic dependence, you can thinking about try to put in a state space model. It's a nonlinear state space model, so you can simplify the calculations. So the observational equation, you can think about those are ut as a Copula type of output, the condition on some state vector and some parameter. So this capital lambda t is a state vector. So the state vector using these simple state transition equations. So that's a general concept. The thing is how to link the state vector to the u. Those are some of the things we did, and that will some sort of enable us to handle the high dimensions. So the theta r just denote the static parameters. So this, in some sense, is a nonlinear state space model. Just try to describe the dynamic dependence. The stochastic Copula model is like this. Basically, what we think about is this P here is try to capture the conditional Copula with conditional time t on the state. And this type of simple model, what you like to do is to measure the correlation, how the correlation evolve over time. So what you like to do is, well, you can use a Gaussian Copula, even though they are not that useful in practice. The student T Copula, those are all relatively more empirically fit the data better. But you can think about those as just some example you can have. In this example, we try to use this well-known Copula to simplify the estimations. But the key point is you like the correlation to evolve over time. We working on the correlation because once you have marginal model, you can transform that, so you can work on the correlation, so that will be easier to handle. So basically, the next slide will tell you how the correlation evolve and so on. So this is a little bit complicated. What I like to do is you can think about the model we have here. The U are governed by some we call the xt. The xt is just a function of the state vector. The lambda are just element of the state vector. We have a common factor zt here. This is latent variable. It's a p-dimensional latent vector. And the epsilon t has the idiosyncratic type of shock. So the loading here, lambda it is normalized, but it can be stochastic in time varying. So that's the things we have. And those lambda tilde is just normalized to make it, remember I said, from the marginal model, you can standardize your observation. So those are just to standardize in this way. So you can think about the unnormalized xt as a function, or the xt is standardized marginal variables. Our observation is y to return, but you can fit the marginal model to normalize that. And the lambda are the loading metrics. Unnormalized lambda tilde is standardized. And lambda I are the unnormalized type of loading vectors. So the state vector is just the vector of this metric, this m by p type of metrics. The constant loading is a special case of what they have. So one of this way, you can link the observation to the common factor and also the loading, the state vector. A simple example is a simple case like Gaussian type of Copula. You can look in this way. So here, what you have, because we understand the inverse of normal is easy, xit is just the inverse of the uniform normal there, and the correlation metric is determined this way. So that's easy to handle in this normal case. It doesn't depend on extra parameter. After the normalization, it's rather simple. You can have a student t, it's just a scale mixture of normal. So this, you draw this inverse gamma distribution to make sure you have a heavy tail distribution. The only thing is now is the inverse depend on degrees of freedom, but otherwise everything seems to be fine, just like traditional way. The key point is you have extreme dependence. The degrees of freedom is to be close to 2. There's a heavy tail, then introduce the extreme distribution like that. Just do you some simulation example to tell you what's going on there. The one on top, there are 4 pictures that generate similarly from the T Copula I just mentioned. The one on top, those are without the idiosyncratic type of noise. So sigma it equal to 0, just a common factor determines that, and you can calculate the correlation. The left one, the correlation is 0.4. The one on the right, correlation about 2/3. You can see that generate the Copula dependent to show up. The one on the bottom, you can also see that, but that is when the epsilon is 0.3. The epsilon here, epsilon it is 0.3, so it's more flexible. You can think in this way. Okay, so that's give you some idea about in the 2 dimension, the T Copula can look like that. You can also, to handle the high dimension, just 1 degrees of freedom is too restricted. So we like to generalize that, allow for the group T student type of Copula. What you like to do is divide the asset into capital G group. A group doesn't have to be the same. The group size can vary, but each group has its own mixing variables. So that's the reason you can do it right in this way. And that's the group T type of Copula. And this seems to be more flexible. Again, for each group within the group. The good thing about doing this group T type of Copula is for the asset within the same group, then it's easy to understand. It just acts like the regular T Copula for asset across different group. Then there's no closed form solution, but you can use simulation to study their properties. Okay, so there's some comment about the model we just proposed. Like I mentioned, this type of thing, the factor structure can simplify a lot of calculations. For example, you have missing value, or you like to do some calculation, and the dimension not really depend on the number of parameters or the asset you have. The dimension really depend on the common factors. For example, you like to take the inverse of the correlations. This will be, the D is easy to do because D is a diagonal matrix, so the inverse is easy to calculate. The thing you have to get the inverse in the center, the P is the number of common factors. If you think about P equal to 1, then that's just a scalar. P equal to 2 is a 2 by 2 type of matrix, so that part is easy to calculate. The determinant is also easy to do because the D is just a diagonal, and the other one is just a P by P matrix. So if P equal to 1, it's just a scalar. So that dramatically simplifies the calculations. So that's the reason that means the factor structure is important. Okay. If you condition on Z, most step we have, even though we have 200 dimensions in our demonstration, all the calculation in some sense can be done parallel because you are reduced to, once you condition on the common factor, the component asset behave rather independently, so you can model that one at a time. So that's, I think, is the good thing about using the factor structure. Okay? So you can, for example, in the data set we have, there's some missing value there. Like for the CDS, not every company every day has a transaction. You have missing value, so you have to impute that, and that can be done because the dimension is low. Also, condition on the common factor ZT. And I already mentioned every asset, it will act rather independently, so you can do that, the single calculation, the scalar type of calculations. The only drawback is likelihood is not known in closed form. Actually, in many cases, involve double integrals. Because you have to, for example, the likelihood function here, you have to integrate out the state vector to obtain that. But even conditional state, some of them, you still have some integral to calculate. For example, the common factor and some other variable, the loading and so on. So it involves the double integral in that sense, a little bit more complicated. On the other hand, this type of problem people has been deal with. For example, use the MCMC method to do the double integral has been proposed before in the literature. We just use that. Okay. The factor model, you can from here just tell you what type of integral involved and how many integral involved that you have to integrate out the common factor. ZT is a common factor. That's the reason you have double integrals. In terms of estimation, I mentioned use a particle MCMC method. In fact, the structure we have, we use a regular type of Copula. So in that sense, you can use a GIP sampling, so the particle GIP type of sampling. The first one is to calculate, you fill in the missing value. And the second one is to iterate, estimate the parameter. Those are basically, you can use the random walk metropolis type of MCMC procedure to do the estimation. You can draw the common factor. That's rather simple because the common factor is a nice structure, under normality structure. Those are easy to do. So step 3, that is simple, is a low dimension. You can easily do that. The complicated part is the number 4. You have to draw the state vector, and those are, we use I mentioned particle MCMC method to do that type of procedures. The detail is given in the paper, so I don't want to describe that in detail here. To simplify the computation, we also make the assumption, say the transition equation is diagonal, and you also allow for the sigma IR identity, and that will simplify a lot of calculations. So in that sense, the calculation is very simple. So let me go to the data set we have to tell you what we did and how to apply this type of methods. So we take the 100 companies. They are in the S&P 500 index. That's easy to do. Their CDS are available. We use the CDS and equity return. The date is from 2008 to the beginning of 2013. There are some date and some missing values. For example, the CDS market open and the stock market open, they are not always synchronized. In some day, there's a CDS, but we don't have the equity, so we get rid of some of those. In any case, it's about 13,000 observations. For the CDS data, we obtain the data from the market corporations. We use a 5-year constant maturity rate. The related issue, we can talk about that, or you pick about 5-year maturity rate. You can pick 3 months or 6 months, but we just pick up 5-year, the maturity rate in our study. There's no restructuring, so it's the X or cross. That means there are no, the CDS, the one we pick, is no restructural constraint to that. The daily changed, so the daily returns. Obviously, in our analysis, we have to change the sign for the CDS because CDS and equity are negatively related. Okay. So we have to change the sign to become positively related. The equity data from the CRISP, we have about 2,800 missing values. It's about 1% of the data missing, so that's really important to impute the missing values. For the grouping, we divide into 14 groups. When we do the group T Copula, we divide into 14 groups based on the SCIC code. So on the average, about 7 firms per group. Now, to give you some idea about the data look like, this is the return of the selected CDS. I only plot 4 companies. Those are in the financial stock. The first one is AIG, American International Group, and the Goldman Sachs, and the Citigroup, and the JP Morgan. I'll give you the CDS. You can see that those are in percentage. CDS can vary a lot. Okay, there's some issue about CDS data. We can talk about that later on. Return for select stock, those are common. We typically see that. Okay, so that just give you some idea about what we have. In terms of model we have, is a high dimension, and it's very hard to check what type of model is available or what is the right model to use. So in the application, we fit 8 models. We fit 8 models, so we can compare with what are available in the literature. We use a Gaussian or group T type of Copula with constant loading. So the loading is constant. That's a simple way to do that. Basically, what people talk about in the literature without the time varying type of loading. We also have the same group type of Copula, but with the time varying loading. So the factor is latent. The loading is also time varying. So that's the 3 model in the second category. Now, in the category 3, we use 2 types of stochastic equal correlation or 2 block equal correlation type of model. Those are basically available by Bob Engel and Brian Kelly. They use this equal correlation type of model in there. If you look at the Bob Engel, the VLab, he actually used the equal correlation type of model to calculate the better risk to rank the financial company and so on. But what we did is we are not using their estimation method. We use the stochastic volatility version of their model and use the MCMC method to do estimation to make it a little more flexible and so on. For the univariate marginal model, we use a stochastic volatility model with leverage and the skewness and so on. So we take for a marginal model, we can obtain the probability integral. And in this demonstration, we only use 1 common factor. So 1 common factor in the analysis. This is a marginal model we have. The top is the mean equations. Okay. So the first term is just to get rid of any serial correlation. For the CDS, the WIT 5 legs of the past observations. For the equity, we use 3 legs. Seems to enough to get rid of any serial correlation in the data. The delta IT and gamma Y, those are the skew, allow for the skewness. The delta IT allow for the skew in the distribution. Delta IT are also for the heavy tail type of mixture type of distributions. So the second equation is the stochastic volatility equation. The delta IT are the scale mixture. So we have that. Low I is the leverage effect. So we have those. So that's the scene we have. We use the MCMC method to do estimation. Because of that, in the stochastic volatility model, we don't have a closed form solution to do the probability integral transform. So use a particle filter to calculate that. That's basically what we have. The last one is we take the 1 minus the UI for the CDS, because CDS is by definition negative related to the equity return. So that's what we have. Here's a summary of the 2 sets. The one on the CDS, the degrees of freedom, and also rho is the leverage effect parameter. Gamma Y is the skewness parameter. Mu is the mean of the stochastic volatility. And phi is the coefficient of stochastic volatility. Sigma H is the standard deviation to the stochastic volatility and so on. The one is the highest posterior probability density interval, 95% interval, to give you some idea. Roughly speaking, even though we allow for the leverage effect is not really that significant. Leverage effect is not that significant. The skewness is also not really that significant. Some equity return shows a little bit of skew, but not by much. And the volatility, they are all highly persistent, about 0.95, 0.97, and so on. So basically, you can see that the degrees of freedom for the CDS is small. It's 5, on the average is 5. So the heavy tail in the CDS and so on. We think there are a couple reasons for this heavy tail type of behavior. One is the observation. Some of the number of observations is small. Basically, what you have is determine how many transactions, how many trade of the CDS for the 5-year maturity you have in every day, and that may be because not too many transactions. So in terms of that, the variability may be big. The other one, we use a 5-year maturity, and you're thinking something happened. People talking about what the probability for a company to file bankrupt 5 years from now, and that can be a huge response as well. But in any case, those are the summary of everyone is 100 company, so every panel based on over 100 company. That's the marginal probability integral. Here you said uniform, those are look reasonable in the sense, those are the stack stock. The one on top, that's the CDS, that's the stock, just to give you some idea about what they look like. Those are the smooth volatility for the CDS of the 4 company I had, and those are for the stock. You can have that, just to give you some idea about that. Now I try to estimate the Copula model. It's a 200-dimensional type of Copula model. The one on the first one is a Gaussian Copula with constant rolling. Lambda is a factor rolling. Then the student T with constant rolling, and the group student T. The group is a 14 group. Remember that? And then the student T with equicorrelation, and student T with 2 block equal correlation. The 2 block is based on the asset we have. We require all the CDS has the same correlation, or the stock has the same correlations. Then they have Gaussian Copula with time varying rolling, student T with time varying rolling, and the last one is the most general, the group student T with time varying factor rollings. We compute 3 statistics. The first one is called the log predictive score. That's IJ Good's idea. And then AIC, BIC of the likelihood function. All those 3 criteria, the small means the model is preferred. The small value means the model is preferred. In all 3 criteria, the group student T with time varying rolling seems to be preferred, even though we have a number of parameters. Okay, so that's the information you can have. Now, one thing I'd like to mention, for the time variant type of rolling, the likelihood function we have here is evaluated at the posterior mean. Also, we repeat that because it is a particle filter in the calculation. We repeat that, use 100,000 particles, and repeat that for 100 times. So those numbers are actually average over 100 times in terms of the actual calculation, because you use a numerical method. So it's not a closed form. Like in the Gaussian closed form, you don't have to worry about that. But for the simulation base, we have to do that. So we average over the number here are actually the average posterior function or AIC number based on 100 time of estimations. The sum result of the group T Copula, that the model is preferred. The number of firms in each category is here. The small one is 4, the larger one is 10. So that's what we have. You can think about degrees of freedom. When you pour them together, the degrees of the small one, I think is a financial stock, is the smallest, is a heavy tail, 12.14. and the larger one is the paper industry. Okay, so we have the oil, food and beverage, and so on. So those are the 100 company we picked. We have this type of information here. Those estimates just give you some idea about what they have, what they look like. Okay, those are to give you some idea about compare with what is available. So the picture here, the one on the far left, is the average Copula model, the posterior mean of correlation of the CDS. So we have 100 company, so we have 100 times 90, about 2 correlations. We just calculate the average of all the correlations. So that one on the red one. The blue one is the correlation estimate by this Angle and Kelly's equi-correlation type of model. They just estimate one correlation, and that is in the blue line. That's for the CDS. The one on the right, the same thing, is based on the factor model and also based on the equi-correlation, 2 block type of equi-correlation type of models. So that gives you some idea about what it looks like. And the one on the bottom is the correlation. The one on top is the mean. The one on the bottom is the correlation, average correlation with their 95% posterior interval to give you whatever information you have. And this one is distributional correlation. The one on the right is the maximum, minimum, 20 percentile, 50, and the 80 percentile to give you some idea about what the distribution or the correlation look like. It's hard to present the result when the dimension is high. So those are some of the select posterior estimated conditional volatility and the rank correlations. So the one on top is a Coke. The title may not be right. The one I think is a Coke. The one that is Coke, the volatility of the CDS, volatility of the equity, and the correlation between CDS and the equities. So that's Coke. The one on that bottom is the AIG. And those are, I think the title got mixed up. Okay. This one is for the Boeing and the Goldman Sachs. So the title got mixed up, but that's the same type of information here. To give you some idea about what he had. So in that case, let me summarize what he did here. We like to use a factor model with stochastic factor loading to model the high dimensional asset return. Basically try to, one application like I mentioned is for the systematic type of risk. We like to calculate the risk of asset allocations. You can do that. And the key idea is the factor structure allow you to handle high dimensions. The calculation is a little bit intensive, but it's manageable because the number of factor is not large. You can do that. Of course, the issue related, there are many issues. For example, which CDS you pick. I picked the 5-year maturity. You can actually have many choices. I'd like to study that. And also, you may want to combine more. You can handle high dimension. We combine the CDS data with the equity data. You can also combine with the options data to pull the information together. That's possible now. How to determine the number of common factors? We use 1. In fact, use 1, we have 200 dimensions to estimate 1 factor. I didn't mention that in reality, this is equivalent to you just use a principal component, first principal component. Because when the panel is high, you estimate 1 factor, and that basically the central limit theorem tell you your estimate close to the average. So that's probably the first principal component. You can do that. Okay. So the number of group, those are our issue we like to do, that's what I have. Thank you.
Thanks, Professor Ray. Yeah, we still have plenty of time for questions if you are not hungry enough.
So when you talk about correlation,
Yeah.
and you're talking about correlation of return after transform before
Yeah.
the copula is nonlinear. Which one?
No, the correlation, I mean, the nonlinear part is because with a nonlinear state space model.
Right.
Yeah, because the distribution, we are on observation. It's not a linear function of that.
Right.
Also, the correlation is not really, we have the state vector. State vector is linear transition, but the correlation is a nonlinear function of the factor, and also nonlinear function of the state vectors. We normalize that. Remember, the correlation is a function. If I can find that, yeah. Yeah, correlation matrix is written in this way. Those are the standardized loading, and the loading depends on the parameter and the state. And those are the reason I mentioned it's not a linear function of that.
So you assume it's diagonal here with the different sectors. Would you willing to assume some kind of sparsity?
The diagonal part is just for simplicity. You can think about the loading. You're thinking about the loading has sparsity. It's possible if I allow for the number of common factors to be large. Since here the number of common factors is small, in our application only one, so we don't worry about the sparsity there. If you say this is a highly structured type of model, this is a very highly structured type of model. If you're thinking about unrestricted, all is unrestricted, then you worry about sparsity, then that's an important issue. But that's different. We didn't consider that. We use a highly structured type of model to model the correlation structures.
Any other questions? If there are no more questions, then let's thank Professor Tsay again. And then it's time for get your lunchbox. Thank you, everybody.